Hey everyone, and welcome to The Explainer. Today, we are going to take one single classic physics problem and use it to crack open a fundamental secret of our solar system. We're going to figure out how scientists can actually calculate the length of a year on any planet. And stick around because by the end, you'll see how this exact method uncovers a pretty surprising connection to one of our closest neighbors.
So it really all boils down to this one simple question. I mean, we all know a year here on Earth is about 365 days, right? But how in the world would you figure that out for, say, Mars, or Jupiter, or even some brand new planet we just spotted? Well, you don't have to guess. Physics gives us the tools to find the answer.
All right, let's get our hands dirty. This is the exact challenge we're going to break down together. It's from a pretty famous collection of physics problems. So, what do we have? We've got a planet. Its mass is just called m, so we don't know what it is. But we do know its speed, a very zippy 34.9 kilometers per second. Our job? Find its period of revolution, which is really just the fancy physics way of saying, how long is its year?
Okay, before we can even think about solving this, we need to gather our tools. Think of it like packing a bag for a hike. For this problem, we really only need two key concepts from our physics toolkit to get a handle on the forces that are keeping this planet in its orbit.
Tool number 1, centripetal force. Now, this can be a little confusing. It's not some new magical force of nature. It's just the name we give to any force that's making something move in a circle. Without it, our planet would just shoot off in a straight line into space. And how much force you need depends on the planet's mass, how fast it's going, and of course, the radius of its orbit.
And our second tool is the big one, universal gravitation. You know, the force that pulls any two objects with mass toward each other. Now listen closely, because this is the most important idea for this whole problem. For a planet in orbit, gravity is the centripetal force. It's the sun's gravitational pull that's doing the job. It's the leash constantly yanking the planet inward and forcing it to move in a circle. So let's get to the crucial step. It's time to connect these two big ideas. This is where the magic happens, where we build the actual mathematical model of our planet's orbit by smashing those two force concepts into one beautiful equation. Let's just lock this idea in, because it is everything. I'm going to say it again. We are not dealing with two separate forces here. For a nice stable orbit, the gravitational force is the centripetal force. The sun's gravity provides the exact amount of inward pull needed to keep that planet on its circular path. Once you truly get that, the math just falls into place. And hey, if those two forces are really the same thing, then their formulas have to be equal, right? So we can literally just set the formula for universal gravitation on the left and make it equal to the formula for centripetal force on the right. This single line of math right here, that's it. That's the complete model of our planet's orbit. The answer we're looking for is hiding right inside.
Okay, hold on a second. Pause. This right here is a classic trap. This is where so many people get stuck. You might be looking at that equation and thinking, wait a minute, the problem never gave us the planet's mass or the radius of its orbit. How are we supposed to solve this thing without all the pieces? It feels impossible, but don't worry. The equation has a really cool secret.
Just look closely at that equation we built. You see the mass of the planet, m planet? It's on both sides of the equal sign, which means we can just divide it out. It completely cancels. And this is actually a huge discovery. It means the length of a planet's year has absolutely nothing to do with its own mass. It only depends on the mass of the star it's orbiting and how fast it's going. A tiny little planet and a massive gas giant, if they're moving at the same speed and the same orbit, would have the exact same year. How cool is that? All right, we've established the physics, we've dodged the trap, now it's time for the fun part, a little bit of algebra. Let's just walk through this step by step to pull out the one variable we're actually looking for, the period.
So here's our game plan. First, we'll simplify that main equation we made after we canceled out the mass. Now, our goal is to find the period, t, but it's not in our equation yet. So in step 2, we're going to rearrange things to solve for the orbital radius, r. Why? Well, because the formula for the period, which you see in step 3, actually needs r. The period is just the distance of one full orbit, which is the circumference, 2 pi r, divided by how fast you're going. So for the final move, our step 4, we take that expression for r that we found and we plug it right into the period equation. And that's going to give us our final beautiful formula for the answer.
And now, the moment of truth. We have our final formula, we have the numbers from the original problem. Let's plug everything in and see what a year on this mystery planet actually looks like.
So, we take that final formula for T. We plug in the gravitational constant, g, which is a known value. We plug in the mass of our sun, also known. And of course, we plug in the planet's given velocity of 34.9 kilometers per second. We let the cosmic dust settle, we run the numbers, and what do we get? We find that this planet's year is about 225 Earth days long.
And here is the absolute coolest part. 225 days isn't just some random answer in the back of a textbook. It's the actual, real-world orbital period of Venus. The mystery planet from the problem? It was Venus hiding in plain sight the whole time. We just used nothing but pure physics to figure out the length of a year on our celestial neighbor. Look, solving the problem and finding Venus is awesome, but the real goal here is to understand the method, right? What's the fundamental strategy you can take away from this and use on other physics challenges? This is it. This is the strategy that works for so many problems in physics. First, you figure out what forces are involved. Second, you set them equal to each other to build your model. Third, you use algebra to solve for what you need, always keeping an eye out for those clever simplifications. And finally, you plug in your numbers and you ask yourself, does this answer make sense? This simple loop, identify, equate, solve, and check, that is your real cosmic takeaway today.
So, I'll leave you with a final little thought to chew on. Based on what we discovered when we were setting up our equation, what would happen to this planet's year if it suddenly became twice as massive but kept the same speed and orbit? The hint is, you already know the answer. Think about it. Thanks for watching.